Welcome back. We are talking about section 5.2, integration by substitution. We're going to continue with this use the method of substitution to find indefinite integrals, but we're going to try out a couple of more, let's say, standard examples than in the last video, where we just kind of got a sense of how things were going to work. So here's our process, and like most of these blue box things, it really doesn't make a whole lot of sense until we try it out. But to briefly summarize what we're going to be up against, we're going to be looking at some integral that our basic strategies, power rule, exponential rule, these sorts of things, aren't going to really handle super well. And the hope is that it's in such a form that if we pick some other variable to represent some of the x stuff, it will simplify the integral. We'll be able to get rid of all of the x's and dx's, replace them with u's and du's. We'll have an expression we can actually take the integral of. We'll do that, and then we'll come back and have x's when we're all done, because u was just sort of going to this land of Oz kind of thing temporarily, and then eventually we get back to Kansas with all of our x's, and our conclusion looks like the form that we started off with, that is, an expression with x's. So we'll try out a couple of different, more concrete examples here. So here, we want to compute this. So in other words, find the family of antiderivatives for this e to the negative x radical thing. Okay, so just to put concretely, observe that if we just looked at power rule and all that stuff, exponential rule, we wouldn't be able to tackle this. So just to go back for a moment to view this, this doesn't just look like e to some power. It's got this extra radical thing. The fact that it's over this expression with a +7, we can't really simplify things over square roots. So if all we had were section 5.1, we'd be out of luck. But it turns out that this is one of the types of integrals where a convenient substitution can kind of get us out of the quagmire here. So now, if we think, well, maybe it's the radical thing that's causing us the most trouble, let's just try the radicand, the piece underneath the radical, and see if that pans out well. So if you recall, the portion that was under the radical was e to the negative x plus 7. And then we do this, so here's our substitution. We also need to look at this derivative piece. So how do these differential terms match up with one another? And so if we take the derivative, e to the negative x is pretty much going to be e to the negative x again. The only catch being that chain rule makes us tack on a negative, so we end up with negative e to the negative x dx. So this is a substitution just for the raw variables. This is a substitution that helps us get rid of the differential, replace dx with du. Now, this isn't super helpful. Well, actually, there's plenty of people who do this replacement just this way. My particular strategy is to go all the way solving for dx, essentially, so that this whole expression can be replaced in the integrand. Okay, so if we go back to our integral, here's the original guy. This is just the statement of the problem from the beginning, and we take a look and say, okay, let's replace all of our expressions that look like u. Let me pick a different color here. We want all of our e to the negative x plus 7s to now look like u. Well, mission accomplished. And then we also want all of our dx's to look like something with du in it instead. Because remember, our rule said, sure, you can get rid of all the x's, but you really got to get rid of all the x's. So not just the x terms, but the dx terms as well. So this was that piece we had up above, 1 over negative e to the negative x du. All of that can be dumped in where dx used to be. Now, if you're feeling clever, you might notice, oh, Mike, why would you put an e to the negative x in the bottom? That's just going to flip up and yada yada. And I'll say, student x, you have a great point there, except that this is actually pretty convenient because I have an e to the negative x in the denominator and e to the negative x in the numerator, and these things will actually cancel each other out. Which is fantastic because all that's left is this negative u, this square root of u, and then this negative on the bottom, so we end up with negative square root of u du. And the great news there, obviously, is this is an integral we can actually compute. All the variables match up, the u's, and match with the differential du's. There's no more x's or mixed match of variables here. So if at this stage of the problem, all those x's didn't go away, then something got messed up. We picked the wrong substitution, or maybe this is not an integral that we can use substitution for. It's not like this is a universal strategy that will always work. It's just one we can try out. You grab your hammer, you try to hit something with it. If it doesn't work, then you grab a different tool. And that's part of what we're doing at the beginning of chapter 5 here, is building that toolbox. Okay, so this integral panned out. We could use our power rule here. This is, well, maybe let's just remind ourselves, this is the same thing as a u to the 1/2 power. And that's convenient because that's going to go up by 1. We end up with an exponent of 3/2. Divide by that, which, back to fractions, but it's the same as dividing. Dividing by 3/2 is the same as multiplying by 2/3. So we end up with that fraction. And then everybody's favorite, our little constant of integration hanging out there. Okay, so this is the portion we're referring to as the back substitution. So we have u, and once we break out of this integral, the u's have kind of accomplished what we wanted them to. I hate to sound opportunistic, but they did what they came for, and now we don't need them anymore. So say your thank yous to our u substitution, and then we can move on with our lives. So this is u, e to the negative x plus 7, and this is actually great. So we no longer have integrals. We have a family of antiderivatives here, and so our mission is accomplished. And we could always check that this actually pans out by taking the derivative of this expression, which is going to involve multiplying by 3/2 and then doing some exciting chain rule, and then seeing that we get the same thing that was inside of the integral to begin with. So a good indication that substitution is the way to go is if this derivative involves chain rule, because it turns out, the inside secret here is that basically substitution is the chain rule of antiderivatives. So unfortunately, chain rule for the derivative you can just apply straight out. It's sort of, the expression tells you when you need to use it. In this case, we have to infer from the structure of the integral, the structure of what's inside, that substitution is a worthwhile strategy. This is another one in a set of ongoing difficulties associated with antiderivatives, basically deriving everything that's worthwhile about them from derivatives. So derivatives get all the cool rules, and then antiderivatives get all the rules that undo those. So they become more complicated just by their nature. Okay, so there's our first successful substitution. We're going to try one more of these before we give up for now. Let our brains rest. So there's a nasty looking integral. All right, so again, maybe it's worth, I'll go back here for a sec, it's worth mentioning that this doesn't just look like power rule. This is also, again, complicated by this radical thing, which we can't really separate these terms out over. So we're kind of stuck as far as clever algebra strategies. So one substitution we could pick would be the entire bottom of this expression. So I'm going to just let this appear here for a sec, and then we'll talk about it so I can show. Here's the integral. If we picked a substitution that represented this entire denominator, so cube root of blah, 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 then it turns out what we would get, and I'm skipping over it because it's not the most effective strategy, is a bunch of stuff that has both u's and x's inside of it. And you're right, yes, look, if you see 4x plus 2 cancels, but then you'd still have this x expression in u's. Again, if you've got your clever boots on today, then you could actually figure out a way to make this work, but it takes a little more effort. So maybe a substitution that just uses the radicand, that is just the piece inside of the radical, the cube root in this case, would pan out. So if we do that, then we pick u equals all that stuff under the radical, so 2x squared plus 2x plus 1, and then do our derivative deal. So derivative of all this is just power rule, so 4x plus 2, derivative of a constant is 0, so it's not going to be a part of this. And then we do our little reorganization thing, so divide by 4x plus 2. I want to reiterate that there are lots of people who just do this. They just use the 4x plus 2 dx and they replace that in the integral. I'm imagining that for a first approach to this, the easiest thing to do would just to be to always solve for dx and then have this expression replace it. But do what works best in your brain. I don't want to circumvent some strategy that works in your head. So again, let's check this out a little bit. We've got all of this is supposed to be replacing dx. So here's where dx used to be, and here's where it is now. We're trying to get rid of all the x's, including dx, and replace them with du's. So this expression still has a 4x plus 2. You might recall we're replacing all of this 2x squared plus 2x plus 1 business, the piece underneath this radical, that's now u. So we'll do a quick check. It doesn't look at first glance like everything's taken care of here. I still see x's and u's, but 4x plus 2 on top, 4x plus 2 on bottom, boom. So now we have an expression that has entirely u's in it. And this is just a copy of that one more time so we can see it. And then all that's left here is our u underneath the cube root, which is the same thing as negative 1/3 power negative because this cube root thing was in the denominator. So bring it up, it's x1, it becomes negative. And this is a perfectly slick integral for us to compute. So it's just power rule once more. So exponent goes up by 1, negative 1/3. We have to be a little careful with fractions here. Negative 1/3 plus 1 is positive 2/3. If we then divide by that new exponent, divide by 2/3, that's the same as multiplying by 3/2. And the ubiquitous plus c, because this is a whole family of solutions, not just one possible function. And then before we go, we say, well, we didn't, the person who asked us this question, here's the original integral. If you answer u, there's no real indication right here, at least, of what this u represents. Sure, you could look back at our work and figure it out. But the most polite thing would be to go back to x's before we're done, because that's the way this question was phrased, was in terms of x's. It's sort of like, you know, somebody says, I've got 10 bucks plus 20 bucks, how much do I have? And then your answer is in euros or something funny like that. Sure, technically correct, but let's actually use the unit that was provided to us in this question. So in this case, x's. I don't know. I feel like we've accomplished something there, so maybe it's worth putting a little box around this, or whatever shape that ended up being. Excellent. So we'll come back in the next video and we'll do one more example, this one involving a word problem, everybody's favorite.